Stay on track with our schedule. Let's do our first binary phase diagram. So X is composition. So now we're going to just do the x-axis is going to be a composition axis, and we're going to only be able to plot one variable in a two-dimensional plot. So we could pick pressure or temperature. So we're going to go with pressure today. Next time when we get back, we'll do temperature. So these are called PX phase diagrams, pressure composition phase diagrams. And so this is when we're mixing things. And so we have this theory of mixing, Gibbs energy of mixing. And if it's negative, obviously it's going to be spontaneous to mix, right? So negative delta G's for any process would be spontaneous delta G's. And so we have this delta G equation. Let me go down here to this one right here. So delta G is equal to delta H minus T delta S. Remember from USHAG, this was the G for USHAG, and it had H minus TS, with delta G is the delta H minus T delta S. That's the governing equation. And if we had an ideal solution where there's really no intermolecular attractions, then we would say that that's an ideal solution, and the enthalpy of mixing is 0. Yeah, we can use the pen. And so whenever we have something like this, I like to say like M&Ms. Right, you put M&Ms in a jar. Let's say you were very meticulous and you put like the red ones in and the green ones and the yellow ones and all of that, so that they were all segregated and color coded. And then you drop the jar and it rolled on the floor. What's going to happen to your mixing? It's going to mess up. Yeah, that's right. If you're meticulous and you spend all the time, it's going to spontaneously mix, isn't it? That's because there's really no attractions or repulsions from the M&Ms. The delta H of mixing is 0. So why does it spontaneously mix? Well, think about this delta S of mixing. This is the equation for the delta S of mixing, and it says it's negative here, but all of these mole fractions, these are mole fractions. All of the mole fractions are less than 1. Therefore, all of the logs of those fractions that are less than 1 are negative. And so that cancels this negative sign out front. So this piece right here is less than 0. Hey, welcome. And so our entropy of mixing is always positive. And if the entropy of mixing is always positive, then we have and if delta H is 0, then we have a spontaneous mixing. So delta G is less than 0. So this is for ideal solutions. Delta G is just that nRT sum of x ln x. So let's get into the phase diagram. So this just says that entropy drives the mixing. And let's say we have a slight attraction of the molecules and they don't want to mix with each other. Temperature is what drives the entropy effect. You see where temperature is in the equation. The higher the temperature, the more negative the delta G. So temperature favors mixing, okay? And that's one thing I always say is when people say oil and water don't mix, I say, well, wait a second, at what temperature, right? Because it'd be at a higher temperature, water and oil will mix, okay? Entropy will drive them together. We'll get into the Hansen solubility parameters later, but this is another like a version of the delta H of mixing based on the solubility parameters. Okay, so after spontaneous mixing, the vapor and liquid come to equilibrium. If we take the Gibbs energy and talk about it in terms of moles, another term for that is called chemical potential. And we like potential energy, right? We remember physics from when we were little, okay? And you've got a ball on a hill. It has potential energy. It's going to want to roll downhill. It's going to want to have a negative change of its potential, right? And so that's why we call the Gibbs energy the chemical potential. So if something is high on the Gibbs energy spectrum, then it's going to want to roll downhill chemically. And so that's a good term for it. Gibbs energy is the chemical potential. Okay, so memorize these 3 terms, or the usages, I would say. When we use XA, we're talking about the mole fraction of A in the liquid phase. And if it's XB, it's the mole fraction of B, obviously. If we use YA, that's the designation of the mole fraction of A in the gas phase. And then ZA is used to designate the overall mole fraction in the vessel, because in this we'll have a vapor region, we'll have a liquid region. What is it in the whole vessel? We'll use Z for that one. If you don't understand those three letters and how I'm using them, then you're going to get totally confused. None of these things have units. It's mole fractions. So these are just like 0.7, right, which is 70% of A or whatever. Okay, let's look at ideal mixtures first. So we have two laws that are associated with this, Dalton's law and Raoult's law. Dalton's law we've introduced already. It's just the partial pressures add together to get the total pressure. And so if I'm right here and I have this composition for A and that composition for B in terms of their partial pressures, then this would be the total pressure. It would be the sum of A and B. Piece of cake. Okay, what about Raoult's law? Raoult's law is this line here and this line here for both substances. Now this is a pretty easy assumption. So this P star comes from the Clausius-Clapeyron equation. So that would be the pure vapor pressure of A at a given temperature. So you find A's boiling point, put that, 1 atmosphere and a boiling point in that equation, and then whatever temperature you're at in the other T, you can solve for P, the vapor pressure at that temperature, if you know the enthalpy of vaporization. Or if you have the Antoine equation, you could calculate it with the A, B, and C constants. And so if we have pure A here, so this is 100% A, then that's the vapor pressure of 100% A. There's no B. But if we start mixing them, and let's say we have 50% A, well, doesn't it make sense that if 50% of the liquid is A, then we'd have 50% of the vapor pressure of A? Because what's at the surface? A may want to leave the surface and come to equilibrium, but half of those chairs are filled with B. And so the vapor pressure of A has dropped because essentially it can't really leave the surface and condense also. The equilibrium has changed. There's half as much A as there would be in a pure case. So it's half the pressure. That's just an assumption to say let's say these things behave like billiard balls coming and going from the surface, and it's like the surface is half as big as it was because we have half the amount of A. The other half is B on the surface. And so here's the pure vapor pressure of B, also from the Clausius-Clapeyron equation for B. And that's the 100% B. So this is 0% A. So that means it's 100% B. I'm using capitals when the letters up there are lowercase, so don't be bothered by that. Okay. Is that bugging you? I'll change them. Okay, here is a lowercase b. All right, that way everything's nice and consistent. Okay, so naturally if this is 100% B and I have 50-50, then the vapor pressure of B would be half of its 100% vapor pressure. So that's Raoult's law, and it's so easy. It's just the mole fraction times the pure vapor pressure. Cannot even be easier. So if I have 30% A, guess what? It's 30% of its vapor pressure. Okay. Yeah. All right. So that's the ideal solution. And these phase diagrams, this is pressure on the y-axis. So we're dealing with vapor pressures. Okay. And this is composition, mole fraction. And so if I change the temperature, all my pressures change, right? So this is a slice through the temperature axis. Like the temperature axis may be going in and out of the board. And this is just one slice at a given temperature. So this is essentially an isotherm. Okay. And so look, if I change the temperature, here's the pressure at 298. It's the blue one at 280. So I cool it down, all the pressures drop. And so then that's the yellow one. And the pressure at 270, it's here. Now this is 1 atmosphere. So let's think about what's going on here. 1 atmosphere. And so that happens to be, this red line happens to be the boiling point of A. How do I know that? Well, look, the pressure, the vapor pressure of pure A, 100% A, is 1 atmosphere. Okay. And so when the vapor pressure is 1 atmosphere, that's what we mean by boiling, right? It's the cavities form and they can stay formed all the way through the liquid. Okay. And so then this mixture here, this orange mixture, so this 1 atmosphere, these are all the boiling points. And so this mixture has a boiling point of 280. And this mixture, the blue mixture, has a boiling point at 298. And so there's something going on here with the mixtures having different boiling points, and we can exploit this to do separations. Now, it's pretty difficult to see, for me, maybe it's obvious to you, but it's pretty difficult to see how distillation works in a px phase diagram. But when we get to the temperature composition phase diagram, the distillation is super easy to see. So we're going to get into fractional distillation when we come back from spring break, and we'll use these phase diagrams to see why the lowest boiling substance comes out first. Okay, but we can kind of pick up on the trends here. Notice this is PA. The boiling point of pure A is 270 degrees, right? That's the lowest of these 3 temperatures that I have here. If I start mixing in B, I'm mixing in something that has a lower vapor pressure, so it has a higher boiling point. In order to get B up here to 1 atmosphere, I've got to really raise the temperature. So the most volatile substance, the substance with the highest vapor pressure, comes out first. So like if I'm boiling this blue liquid, the vapor that's coming out is really strongly A. There's a lot of vapor of A at that temperature. And there's much less vapor of B at that temperature. So we can kind of see how separations might work here. Okay. Now we also see too that composition affects the boiling point. It also affects the melting point. And so when we get to solid liquid phase diagrams, we'll see how the melting point is a good test for the purity of a substance. So when you did the organic melting points, you did a synthesis, you recrystallize to purify it. You get a melting point, you want a really sharp melting point. We're going to learn about that in a couple of weeks. Okay, let's look now at the vapor phase composition line. This is where it kind of breaks your brain a little bit. So let's pick a spot here and look at this, and we'll call this ZA. And I'm going to get right here in this region, and I'm going to pick that spot right there. Come on. Okay. So I'm right at 50-50 ZA. So ZA equals 0.5. But look at this red line. This red line is the YA composition line. The black line is the XA composition line. So we have, again, an equilibrium between 2 phases inside this. So this is a 2-phase region. What do you want to call that inside this slice? I don't know. This swoop. Good. So if we're right here, what is ZA? Or let's review. I said to memorize that. What is ZA? Yeah, so in the whole container, we have 50-50 in terms of moles. But if I'm at this pressure, so I've got the whole container in equilibrium at this pressure, which is slightly above 1 atmosphere. I've got it sealed up, so I'm holding pressure. The vapor phase has this composition, and the liquid phase has this composition. So the vapor phase is like 55% A, and the liquid phase is 45% A. And that makes sense because A is more volatile. A has a higher vapor pressure. So the vapor phase should be enriched in A. It's the more volatile thing. And because A went to the vapor phase in a higher abundance, the liquid phase is depleted in A. So it's at 45%. So the more volatile substance evaporates more, okay, in these mixtures. Okay. And that's how we separate them. If we could get them to go up a tube and then maybe run them through a water-chilled area, we might be able to get them to condense, and then we could separate A. And that's a great idea. Let's go to organic and make it happen. Okay, so that's what a fractional distillation does. So the composition, this is the take-home lesson, compositions of the liquid phase and vapor phase are not the same. Okay, that's how distillation works. We heat up the liquid, it starts boiling, and the vapor is enriched in the higher vapor pressure piece, the substance. So this is a map of the compositions of which each phase is stable. Okay, so this is just restating the same thing, showing that you've got XA and YA at that 1 atmosphere point, and they drop down. Let's look at dissimilar liquids. So this is for ideal solutions. Let's look at non-ideal solutions. So this is carbon disulfide and acetone. So there are substantial deviations from the ideal partial pressures. Okay. So think of the intimate contact that the molecules have in the liquid phase. So they have a lot of time to interact, and so there's those small interactions between the molecules have a huge effect on what happens above the liquid. So here's changes to to Raoult's law. So remember, this is Raoult's law. This dashed line right here, Raoult's law. I'll say this is actual, and then this is Henry's law right here. So Raoult's law was super easy. The pressure of A is equal to XA times PA star. Henry's law, well, it's not going, notice it's not going all the way across to P star, it's going to some other place on that axis. And so we're going to call that Henry's law constant, KB. So this is saying that P of A is equal to XA times KB. Oh gosh, for goodness sakes. I don't know why I did that in the notes. Let's change these to B's. Notice that the mole fraction, it's now mole fraction of B. I just pulled these charts from the book, and it changed the A's to B's. So now we're talking about substance B. Okay, so let me change these all to B's so that I don't confuse the crap out of you. All right, so this is the pressure of B is the mole fraction of B times the pure vapor pressure of B, or the vapor pressure of pure B. And for Henry's law, the pressure of B is the mole fraction of B times the Henry's law constant for B. Now this is the Henry's law constant for the mixture of A and B. So every binary mixture has its own Henry's law constant. That's a pain. So if I have a chloroform in water, there's going to be a KB for chloroform when it's in water. And if I have a chloroform in ethanol, there'll be a KB for chloroform and ethanol, and one for ethanol and chloroform. So each substance has its own KBs as it behaves in another substance. And the actual is pretty hard to predict, this middle region, okay? But notice the limits are pretty good. This limit is following Raoult's law, isn't it? And down here, this limit is following Henry's law. So there's regions where we can use Raoult's law and regions where we can use Henry's law. So let's focus on the limits. Dilute solutions of B are dominated by the properties of individual particles of B. Okay, concentrated solutions of B are dominated by the properties of liquid B. So if you have a dilute solution, B is already kind of acting like a gas. It doesn't know there are other B atoms around or molecules. It's just already dispersed, and so it may come out of solution a lot more. Okay, and in this case, it comes out a lot more. The actual vapor pressure is much higher than the ideal vapor pressure. The concentrated solutions of B are almost like pure B. So we just got a little bit of A sprinkled in there. It's like what I call dirty B. Okay, it's mostly B. There's a little contamination in there. Okay, sounds like a rapper, dirty B. Okay, so Henry's law. I was thinking of what's her name. Yeah, there you go. Or Sexy Red or whatever. Yeah, so, yeah, dirty B. Yeah. So Henry's law. The partial pressures of the solute depends linearly upon the mole fraction of the solute, but the proportionality is not the vapor pressure. Okay, if B is the solvent, then this is Raoult's law. If B is the solute, then we use Henry's law. Those are the equations I wrote on the previous slide. Okay. I'm going to have to kind of go a little quick so we can reach a stopping point. So the ideal solutions, then, if it's an ideal solution, KB equals the P star for B. If they're really, really different, you know that mixture is not ideal. So you can always look at the KB value, and some of them are like 10 to the 5th. I mean, they're huge, and the vapor pressure is pretty small. So let's look. Tale of two mixtures. It's kind of like a tale of two cities, right? My literary joke for the day. Look on the left. The one I showed you before was carbon disulfide and acetone, and then on the right is chloroform and acetone. So think about my two statements about these. Look at the one on the left and listen to what I say about it. Carbon disulfide and acetone hate each other. And then look at the one on the right. Chloroform and acetone like each other. So do you get that from those two diagrams? And if so, how? Help me explain my evaluation that carbon disulfide and acetone hate each other. They both have non-ideal behavior. So Henry's law applies to both sides. But what is Henry's law? How is Henry's law different in the left and the right? That you're onto the right thing. So look at Henry's law constants and tell me how I can assume or I can interpret these to say carbon disulfide and acetone hate each other, and or you could just focus on the total vapor pressure line. So the Dalton's law line, the very top dark line for both. So the one on the left. This is the ideal Dalton's law right here. And this is the actual. And over here on the right, the ideal Dalton's law is this one, the straight one, and the actual is there. That's right, over and under. Yeah. So what does it mean in the carbon disulfide acetone that the actual pressure is so much higher than the ideal? That's what I'm saying. They don't like each other. So let's take a 50-50 mixture and I put them together and they hate each other. So they're going to the gas phase where they don't have to interact. Right? In the liquid, they're interacting, they're touching, they're like, yeah, I don't like it. So they go into the gas phase where they don't have to interact. And it's interesting, the vapor pressure of pure acetone is right here at whatever torr, say 300 torr, 350 torr, but the actual maximum vapor pressure is like 450. So it's 100 torr more than what you would predict from the Dalton's law, Rauch's law. So, I mean, that's 30% high. 30% more vapor pressure than you would expect. That's a significant difference. We're not talking about 2%, 30%. They really don't like each other. Whereas over here, the vapor pressure of, see, we're talking about chloroform on the x-axis. So this is chloroform, the pure vapor pressure of chloroform. I mix them together. So that comes across here. That's like 270. And I mix them together, and at this point, the vapor pressure is about 250. I mean, it's not huge, but that's like 15% low. So they like each other. So you put these mixtures together, and the pressure of the gases actually decrease. They want to go into liquid. They like each other. Does that make sense? It's kind of interesting to me. Okay. Now, what's going on with acetone and chloroform? You've got chloroform, CH3 or Cl3, CH, and then acetone has that carbonyl. So notice chloroform by itself can't hydrogen bond to itself. It doesn't have a carbonyl or a nitrogen. And acetone by itself really can't hydrogen bond. It's just got methyl hydrogens. They don't really hydrogen bond that well. But you put chloroform and acetone together, hey, we got a partner now. It's a dance. Okay, so they team up, they hydrogen bond, and they're happier together than they were apart. So their vapor pressure is lower than the pure substances. Whereas chloroform and carbon disulfide, acetone has a dipole moment. Carbon disulfide doesn't. Okay, so if I start putting carbon disulfide and acetone, I have to get the dipole moments apart. And if that carbon disulfide leaves, then the dipole moments can line up. And so acetone's excluding the carbon disulfide. When it leaves, then the acetone can form dipole moments. Yeah. So this is just we're thinking in terms of molecular views, right? How are these molecules interacting in the liquid phase? So that's what's governing this vapor equilibrium. And so here's some experimental data on the carbon disulfide acetone one. And these deviations from ideal are we call them activities instead of vapor pressures or pressures. So we have these activities, and there's this activity coefficient gamma. So we just correct our equation by adding another variable, which is what we do in science, right? And this activity coefficient is just the mole fraction of the activity divided by the mole fraction. And so these activity coefficients, they are a function of A, so it's not a single constant. It's different for every composition. Very difficult to arrive at those from a theoretical standpoint. This is one option, this Margulies equation, where you can put in this beta parameter, and you can model, situations where they hate each other and situations where they like each other. Okay, so anyway, that's activities modeled with the Margulies equation. And then we'll get into this lever rule problem when we come back from spring break. But this is that deal I did with the Z composition, and as you move through this two-phase region, you have the lever rule. So think about a seesaw. We don't have seesaws anymore, but got a little kid over here. Okay, and then they got me over here with a big old belly. Okay. Right, and so that means there's more of this, right? Because look where the fulcrum is. So if you want to get that seesaw to balance, the fulcrum, the line that's closest to the fulcrum has most of the moles. Okay. All right, so what's that?